Okay, moving on to the next chapter, stereochemistry. Now, hopefully you're really good with Lewis structures, really good with VSEPR theory, and you can really see the three-dimensional shapes of molecules, because that's what we're going to be dealing with this entire chapter, and truthfully, from here on out, we'll always have to worry about this concept of stereochemistry. Now, here's the idea. Stereochemistry starts with this, and we'll go through some definitions in a minute. But look at these two molecules. When we see them and we look at them, we say, okay, there are two black carbons here. We've got this is a methyl group here. So we have a methyl group here, and this carbon has a hydrogen on it, a red group, and a blue group. And then if we look at this molecule here, we can see, well, wait, this middle carbon has a methyl group on it, a hydrogen, a red group, and a blue group. So these two have the same formula. Two carbons, 1, 2, 3, 4 hydrogens, a blue and a red. Two carbons, 4 hydrogens, a blue and a red. Same formula, so they are isomers of each other. The difference is between this and other isomers we've looked at, it's the same connectivity. Okay, this has a methyl group, a CH3, here's a CH3, same connectivity. The methyl here is bonded to this carbon. This methyl is bonded to this carbon. What is this carbon bonded to? It's bonded to a hydrogen, a red, and a blue. What is this carbon bonded to? A hydrogen, a red, and a blue. So they have the same connectivity. Each atom in this molecule is bonded to the same atom in this one. This central carbon is bonded to four things: a methyl, a hydrogen, a blue, a red. Over here, a methyl, a hydrogen, a blue, and a red. So they have the same connectivity here, but are they the exact same molecule? They look pretty similar, but if you notice, this one is the mirror image of this one. If there was a mirror right where my pointer is, right here, you could see that this right here is the mirror image of this. And, okay, I turn it this way, turn it this way. Yes, you can still see they are the mirror images of each other. Now, this is something very important, and we'll talk about it again. Even if I turn it like this and have these two like this, I can ask, is this molecule the mirror image of this molecule? The answer is yes, it is. This one is still the mirror image of this one. Just because you've decided to put them in an orientation that doesn't show that is not the fault of the molecule. All right, there exists orientation. You can just rotate this molecule to some orientation where the two are, you can actually see the mirror image. Means that even if it's not in that orientation, even if it's something like this, the fact is this molecule is the mirror image of this one. This has to do with something we call handedness or chirality, just like your left hand is the mirror image of your right hand. But something else about these mirror images of these two molecules, they are not superimposable. Meaning there's no way to rotate this molecule and get this exact one. Because, well, let's look at it. See how I've got the reds down at the bottom, the blues on the top? Well, can't I just rotate this single bond? And now the red's at the bottom and the blues at the top? Well, yeah, but here the hydrogen's coming up, but here the hydrogen's going back. So, yes, I rotate that bond, but I did not get this exact molecule, this exact orientation. All right, so if I want to try to superimpose these, I can say, all right, if I put them together like this, I can see, okay, my methyl groups are overlapping, my hydrogens are overlapping, they're at the same spot, but the blue and the red are not at the correct spots. If I switch it so the blue and the red are at the right spots, okay, blue and the red are at the right spots. Well, how do I do that? How do I get the blue and red to be at the right spots? Here we go. There. Now the blue and the red are correct because the blues are together and the reds are together. But now the methyl is overlapping with this hydrogen, and the same thing over here. The methyls and the hydrogens are in the wrong spot. So if I get the blue and the red in the right spot, the methyl and the hydrogens are at the wrong spot. If I get the methyl and the hydrogens at the right spot, the blue and the red are at the wrong spot. There's no way to do it. I can get the hydrogen and the red to be at the right spot, but now the blue and the methyls are at the wrong spot. So there's no way to turn this one to get this one. These two molecules are non-superimposable mirror images of each other. Therefore, they are different molecules. And we're going to find out in a little bit. That means we're going to have to give them slightly different names. But these two are different molecules. All right, let's pull these aside and let's go through some definitions. Okay. Stereochemistry. The first thing we're going to look at is something called chirality. Handedness. That's what we've just been talking about, the non-superimposable mirror images. Now, technically, the proper English word is non-superposable, but we still use non-superimposable because it just sounds better to chemists. Non-superimposable mirror images, they are biologic. This non-superimposable mirror image chirality here has biological significance. Okay. Stereoisomers. These are not constitutional isomers, meaning they have different groups, different places in the molecule. They have atoms connected in the same sequence. They have the same connectivity, but a different arrangement in space. Just like we saw before, the carbon atom here is bonded to the same three things that this carbon atom, or same four things that this carbon atom is bonded to, but they're just arranged differently in space. So a stereoisomer is any two molecules are stereoisomers if they have the same connectivity but different arrangement in space. Enantiomers are stereoisomers that are non-superimposable mirror images. So this guy is the mirror image of this guy. They're not superimposable. These two are enantiomers. Diastereomers are all other stereoisomers that are not mirror images of each other. So the prime example of diastereomers are cis and trans isomer. Note that you look at this carbon up here, it's bonded to a chlorine and a hydrogen, same as this one, chlorine and a hydrogen. But here, this is bonded to a chlorine and a hydrogen. This carbon down here also bonded to a chlorine and hydrogen. But here the two chlorines are cis to each other. Here the two chlorines are trans to each other. It's a double bond, so we cannot get rotation. Same connectivity, different orientation in space means these are stereoisomers. Same connectivity, different orientation in space. Stereoisomers. They are stereoisomers. But because they are not mirror images of each other, they cannot be enantiomers. So if they are stereoisomers, but they're not enantiomers because they're not mirror images, they must be diastereomers. These are diastereomers of each other. For example, let's look at these two right here, where Me stands for methyl. Here I've got a ring. Recall, ring means that this single bond here cannot rotate. Two methyls cis to each other. Here are two methyls trans to each other. There's no way to rotate this methyl up here. So do these guys have the same formula? Yes. Do we have a different arrangement in space of the atoms? Yes. Are they mirror images of each other? No. So these two must be diastereomers. All right, more definitions. Chiral molecule, molecule that is not superimposable on its mirror image. Means it's one of the enantiomers of the two enantiomers in the pair. So these two molecules here are enantiomers. Each one is a chiral molecule. This is a chiral molecule. It is one enantiomer. It is a chiral molecule, meaning it has a non-superimposable mirror image. Note, the non-superimposable mirror image might not be anywhere around. It's just that it has it. When you look at the molecule, you realize, oh, this thing has somewhere out there, one could possibly build the non-superimposable mirror image of this molecule. All right. So if it's not a chiral molecule, then we say it is achiral. So here's an example of 2-butanol, where you just have, okay, here's our molecule. We have an ethyl, and well, here's our butyl group. The second carbon has the OH on it, the hydroxyl group on it. And when we draw that, we realize, well, when we drew it this way, we didn't really look at the 3D orientation. The question is this OH coming out at us or going back the other way? Okay. So let's look at this molecule. We can build it. And let's see. You might be noticing it's going to be very important in this chapter for you to have molecular models so you can build these. So we have this ethyl group. This carbon right here has an ethyl group coming off of it. Ethyl. It has this methyl group coming off of it. It has this hydrogen and this oxygen of the OH going backwards. Because I made this one right here with the OH going backwards. I could have made the OH coming forwards. Here, when you three-dimensionally build the molecule, the OH either has to be going back this way into the page or coming out towards us like this hydrogen here. So the question is, oh, can't I just make this OH coming out at us just by turning the molecule over? There, now the oxygen is coming out at us. But question, with the oxygen coming out at us, did I actually make this molecule here? No, because we can see, let me line them up. Yes, the OH is coming out at us, just like in this molecule. The hydrogen is going back, but this molecule has the CH2, CH3, the ethyl group on the left. Here the methyl is on the left. The drawing has the methyl on the right, but here the ethyl is on the right. So just by flipping this molecule over, I cannot make the other molecule. I can draw it pretty easily, just draw the OH back with one of them, draw the OH coming out with the other one, but when I make the molecule, I see that there's no way to turn this one, the one I made first, there's no way to turn it or rotate it to get this one here. So that means this simple molecule, 2-butanol, is chiral, because I've got this guy. In order to make the other one, I have to make the non-superimposable mirror image. The mirror image of this molecule here is non-superimposable upon this one here. All right. And note, these two, as drawn, are enantiomers of each other. Two chiral molecules, they are enantiomers of each other, even though they're not really drawn as mirror images. Can you see that if you took this second molecule here, rotated it 180 degrees, put the methyl on this side, the ethyl on this side, that's how we're going to rotate it around, that this OH would be going back and this hydrogen would be coming out after we've just rotated the molecule 180 degrees, and can you see that it would be the mirror image of this one? Okay. So the question then is, how do you know if a molecule has a non-superimposable mirror image? How do you know if it's chiral? In organic chemistry, there's one really nice way. This doesn't cover all of our bases. It doesn't cover every possibility, but it covers most of them. You find enantiomers with a tetrahedral carbon, so it must be an sp3 hybridized carbon that has 4 groups coming off of it. And here's the deal. It must be 4 different groups coming off of that carbon. So note, this carbon here has 4 different groups coming off of it. It's got an ethyl. It's got this ethyl over here. This ethyl, the methyl, the OH, or the oxygen here, and the hydrogen back here. Note, I know that this is a carbon and this is a carbon, but this is the carbon of an ethyl group, this is the carbon of a methyl group, and ethyls and methyls are different. So if this were a methyl group over here, if there were two methyl groups on here, then this carbon would be bonded to an oxygen, a hydrogen, and two of the same methyl groups. It would not be a chiral carbon. You could draw the mirror image of it, but you could actually rotate the mirror image and come up with the exact same molecule. All right. So, carbon that has 4 different groups coming off of it is a chiral carbon. We call it an asymmetric atom or a stereogenic atom or a stereocenter, or as IUPAC calls it, a chirality center. All right, we will continue on with this in the next video.